Welcome to this video on the anatomy of SQL injections. We will explore the methodology, common attack vectors, and exploitation mechanisms known as the kill chain. This content is designed for blue and red teams, penetration testers, and developers. A SQL injection occurs when input is not properly sanitized, allowing attackers to manipulate database commands. While a legitimate process expects simple data like a username, an attacker can input malicious syntax to alter the logic of the query and bypass authentication. The attack follows a three-step kill chain. First, reconnaissance and discovery. Second, executing the attack. And third, advanced exploitation. Each step increases the attacker's level of access, moving from simple requests to full network compromise. In the first step, attackers map entry points, examining URL parameters, HTTP headers, and hidden fields. Tools like Burp Suite and TamperDev are commonly used to intercept and modify these requests during the reconnaissance phase. Next, the attacker performs a triage by analyzing the server's response. Error-based responses reveal database types and structures, signaling an opportunity for in-band attacks. Conversely, if the server hides errors, attackers use blind SQL techniques to extract data indirectly. This matrix classifies attacks by family, technique, and complexity. In-band attacks are fast but visible in the UI. Blind or inferential attacks rely on side effects like time delays, while out-of-band attacks force the database to send data to a controlled server. In-band attacks often utilize the union operator. To succeed, the malicious query must have the same number of columns as the original. Attackers typically use order by commands to determine the correct column count through trial and error. Blind SQL injection relies on logical decision trees. Boolean exploitation analyzes content changes based on true or false conditions, while time-based exploitation measures server delays. These methods often require thousands of requests, making automation essential for the attacker. The third step involves privilege escalation and interaction with the operating system. Databases may have built-in functions, like MS-SQL's XP_CMD shell, that allow direct command execution or the creation of web shells to gain persistent access. Attackers may also target system tables to grab passwords or create database triggers. These triggers can maintain persistence within the database structure, ensuring that unauthorized actions continue even after the initial injection is resolved. Tools like SQL Map automate these complex attacks. With a single command, it can identify database structures, dump tables into CSV files, and even support advanced features like out-of-band reverse shells, significantly increasing the efficiency of the exploitation. To evade WAF and IDS systems, attackers use techniques like string concatenation, inline comments, URL encoding, and case variations. These methods help bypass signature-based filters that would otherwise detect and block malicious SQL patterns. Syntax varies significantly across different database management systems. Attackers must adapt their payloads based on the database type identified during the reconnaissance phase, as there is no universal magic payload that works in every environment. The primary defense against SQL injection is the use of type-safe parameterized queries. This ensures that user input is treated as text rather than executable code. Secondary defenses include strict input validation, minimizing database privileges, and disabling dangerous features. In conclusion, SQL injection is a preventable vulnerability. Success for security teams lies in mapping all entry points, while developers must prioritize secure coding practices like parameterization and the principle of least privilege in their software architecture.